This is Geometry A, Unit 6, Lesson 8. We're proving converse parallelogram proofs. Converse, you might recall the word converse. We used it when we talked about logic last unit. The converse of a statement is when you take the hypothesis and conclusion and switch them around. So we learned that if you have a parallelogram, then opposite sides are congruent. The converse of that statement would be if opposite sides are congruent, then you have a parallelogram. There are a number of rules or theorems by which you could prove something is a parallelogram, and here are some of them. If opposite sides are parallel, you've got yourself a parallelogram, because that's the definition of parallelogram. If opposite sides are congruent, you've got yourself a parallelogram. If opposite angles are congruent, you've got yourself a parallelogram. If opposite angles, if the diagonals bisect each other, you've got yourself a parallelogram. Okay, diagonals. Takes me a little while to draw the diagonals. If the diagonals bisect each other or split each other in half, you've got yourself a parallelogram. So once again, if the diagonals bisect each other, you've got yourself a parallelogram. Okay? There's one more that the unit doesn't really mention that I noticed, and that is if one pair of sides are both congruent and parallel, you've got yourself a parallelogram. But also if the adjacent angles are supplementary, that is, add to 180, then you've got yourself a parallelogram. This can really be thought of as a corollary to this one right here, if opposite sides are congruent. Because if adjacent angles are complementary, or supplementary, they add to 180, then the opposite angles are necessarily going to be congruent. It can be proven. So those are the 5, or actually 6 rules for proving something is a parallelogram. And each one of them can be proven. And we can write a separate proof for each one. I'm not going to write a separate proof for each one, or even attempt to do so. We could do so, but it would take a lot of time. I'm going to prove 1 or 2 of them, maybe 2. We'll see what time we have. Okay? So let's start by drawing a quadrilateral that is not necessarily a parallelogram. And we're going to prove it is a parallelogram. So let's start with this shape right here. Okay, and let's say we know that this side is congruent to this side, and this side is congruent to this side. Let's label it so we can refer to it, A, B, C, D. So prove that a quadrilateral with 2 pairs of opposite congruent sides is a parallelogram. So we were given A, B, C, D such that AB is congruent to CD and BC is congruent to DA. Okay. Draw diagonal, and I'm going to draw a diagonal BD. It's really arbitrary which one. I draw. I'm going to draw a diagonal BD. Okay, you can recognize the triangles, and we're going to use our triangle proof theorems here. So we may notice they share a side, so BD is congruent to BD by, remember the doctor hitting your knee with a rubber mallet, the reflexive property. Okay? Okay, and so the two triangles seem to be congruent through 180-degree rotation around the center here. By side, 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 we have a side congruent to a side congruent to a side congruent to a side. So triangle ABD is congruent to, now you got a picture it rotated, ABD goes CDB, CDB, triangle CDB, by side, side, side. Now if triangles are congruent, so are their parts. So that means angle CBD is congruent to angle ADB. It also means that angle CDB is congruent to angle ABD. So angle CBD is congruent to angle ADB, ADB, and angle, now I said CBD, CBD, oh, no, careful, I did that wrong. CBD is ADB, ADB. I may have done that right, actually. And angle ABD, it's hard to keep these letters straight, is congruent to angle CDB. Since we just proved they're congruent, corresponding parts of congruent triangles are congruent. Okay, now what have we just proven? We have just proven that if we have these two angles congruent, that we call alternate interior angles, the lines are parallel. So therefore, BC is parallel to AD, and segment AB is parallel to segment CD by, and this is not the alternate interior angle theorem. That would state if parallel, then alternate interior angles are congruent. We're doing the backwards of that, the converse. So by the converse of the alternate interior angle theorem. QED, quad erat demonstrandum. I said it, therefore I proved it. And let's review what we just learned. We just proved that if you've got a quadrilateral where two pairs of opposite sides are congruent, you have a parallelogram. Because that would also mean, since we can divide it into two congruent triangles and the corresponding parts of triangles are congruent, alternate interior angles are congruent, the sides, opposite sides are parallel, which meets the definition of parallelogram. All right. And I'm debating whether or not to do the next one. Yeah, I think I'll give it a shot. All right. So let's do the next one here. Okay. So we want to prove, and I'm just going to sketch for the sake of time. We want to prove if we've got a quadrilateral where the diagonals bisect each other, then we've got a parallelogram. Okay? And yeah, I think we can do this. All right, let's label it A, B, C, D. Okay. So prove if prove a quadrilateral with bisecting diagonals is a parallelogram. Okay, so this is another one of the converse rules. We've already proven that if the diagonals, if you have a parallelogram, the diagonals bisect each other. We're going to do it backwards now. Going to end with, start with the diagonals bisecting each other, end with it being a parallelogram. Okay, so we were given VE is congruent to DE, and AE is congruent to CE. That's part of what we were given. Okay. And here I'm going to use a rule that we haven't talked about in these videos yet. This angle has got to be congruent to this angle. Okay, so angle BEA is congruent to angle DEC. Though we did talk about it in a previous lesson, just not in this unit. BEA is congruent to angle DEC by the vertical angle theorem. Vertical angles, they're known as vertical angles. Okay. All right, so look at what we've got. We've got a side congruent to a side, an angle congruent to an angle, a side congruent to a side. We have side, angle, side. So triangle ABE, again, looking at it by rotation, ABE, ABE, CDE. Triangle congruent to triangle CDE. Okay, by side, angle, side. Now corresponding parts. This angle, angle B, or angle EBA, or ABE, is congruent to angle CDE. Angle ABE is congruent to angle CDE. And, because I'm going to use the same reasoning, same logic, so I'm going to list them in the same step. And angle BAE is congruent to angle DCE. Angle BAE is congruent to angle DCE, since corresponding parts of congruent triangles are congruent. Okay. All right, there we have it. Now we've got some parallels. So we've got this situation going on where we just proved that, actually what we just proved is this situation. I only needed one of those, actually. Right? So we just proved that these two sides are parallel. So BA, or AB, is parallel to CD by the converse of the alternate interior angle theorem. I'm going to abbreviate. Alternate interior angle theorem. Okay, I'm going to cut this a little bit short because now we'd have to go through the same argument for triangle BCE and ACD to prove that BC is parallel to AD. But the steps are the same. So dot 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 BC is parallel to AD for the same reason. And that satisfies the definition of parallelogram. So therefore, ABCD is a parallelogram by the definition of parallelogram. QED, quod erat demonstrandum. We set about to prove it, and we proved it.